All right, so sketch figures, find the arc length and the area of each of the following. It's all formula based. And you know what I can do? So R equals 3. Now, in theory, you should not need any calculus-based formula to figure this one out, because R equals 3 is a circle with a radius of 3. If you know that piece of information, you're pretty good to go. But let's use our newfangled technique here. Let's see if that's gonna be a rewarding approach. All right, so I left it on huge print, not what I want. Integral 1/2 r squared d theta, going from a to b, alpha to beta, but we'll say a to b. All right, they gave us bounds. That's good, because I need bounds for my definite integral. So I'm looking at, on the interval of 0 to 2 pi, 1/2 3 squared d theta. And again, this is area. Just thinking about something. Anyway, so now we can clean it up. That's going to be 9/2 d theta. As integrals go, this is not a terrible one, right? Because we're anti-differentiating with respect to theta, and it's constant. So I'm just going to introduce a theta. All right, so I know if I plug in a 0, I got to plug in the 2 pi first, then the 0, but I know if I plug in the 0, it's going to give me nothing useful. So 9/2 times 2 pi would give us 9 pi. Nine halves times 2 pi gives us 9 pi. So if I tell you, again, that this is a circle with the radius of 3, and the formula for the area of a circle is pi r squared, you should have been expecting 9 pi to begin with. Now, it begs the question, well, would I have to do all this stuff to get credit? Well, I would be, from a student standpoint, I'd be looking forward to a question like this on a test. I would want this one. Yeah, I'd be happy to do all this work to get that answer. I know I could get it with pi r squared. I would want this question for 2 reasons. One, because it keeps me from having to do a harder question on this topic. All right, all skills are there. You know you have to take an antiderivative, use a formula, and so on. All right, the other thing is, you already know what the answer is supposed to be going into it. All right, if I give you something that's completely unfamiliar, like a Lima song, hopefully I got that right, you have no sense going into the problem what the area is supposed to be. I don't know that I want to do arc length yet with this, because let's do the area for the second one first, and then we'll get into the arc lengths all in one shot. All right, we'll go that way. Just because I think it's going to ruin my flow here. Yeah, to get the, yeah, so if you were, is it like Math 9? Yeah, totally. Yeah, my standing rule, for those of you who are unfamiliar with my way of doing things, is if it's a definite integral, you don't have to show me anything except for the answer. So depending on the instructions, you may have to have it in terms of pi, so you might have to wiggle around that, but I don't need you to actually show me the anti-differentiation technique. All right, there's going to be enough opportunities for me to assess you on your ability to take derivatives and antiderivatives in this course. So you're not going to have to worry about, like, if you have something like this, just pop it in your calculator. It's going to spit out like 29 point whatever. You know it's a multiple of pi, so divide out the pi, and you know, like we talked about last class. So good point. And most of the time it's going to call for a decimal answer anyway, so you'd be all right. Now, for number 2, recommendation for this question, take a quick peek on the calculator and see what's going on first before you even start the problem. All right, so if I were to graph this, and again, it's just a quick peek. I'm popping in 2 plus 4 times the cosine of theta. Quick zoom 6. All right, just to get it going. Adjust your domain. So theta min, theta max should correspond with what the problem says. It says 0 to 2 pi. That's what I want. All right. So then, all right, we got that. What I need you to do, though, is make sure that this is not going to loop around more than once. All right, because what will happen is it'll go around one time, and then it might start tracing over it again a second time. All right, if that's the case, when you go to use your area formula, it might give you an overestimate of what the area is. It might give you double the area, right? It could be terrible, right? So how do you make sure that you're going far enough? Well, there's a couple of ways. One way to be, like, I don't know, is like cavalier about it, would be to put it on bold and just have a keen hawk eye, like stare at it intently. Okay, I don't think it went around more than once. The other way to do it, 2 plus 4 cosine, which is a little bit better, a lot of it better. Take your theta max, which you know is supposed to be 2 pi, and dial it back a smidge. All right. If you dial it back a smidge, then your graph should be a smidge short of being completed. All right. It should leave a tiny little smidge of a gap. So instead of 6.28, I might put 6.2 and hit graph. Leaves it slightly incomplete, all right, telling me that 2 pi was an appropriate endpoint for this, that I needed to go to 2 pi in order to close the loop, all right? Because if let's say the domain, and this is the basis of any kind of trick question I could give you. And most of my trick questions happen based on typos that I chose to just leave and keep them as trick questions. Like for a problem like this on a test, it might be this exact question, but maybe 0 to 5 pi over 2. So 2.5 pi. So you're going overboard by half a turn, I guess. Well, a quarter of a turn, right? So let's say I put 3 pi in here. It's hard to see that the motor is still running, you know, that it's still going afterwards. But if I were to dial it back, you know, let's say I had 3 pi given. I'll dial it back to like 9. It's still a complete graph. Dial it back to 8. Still a complete graph, which means that my domain is too expansive. All right. Now, this is the difference between arc length and area, because in arc length you might want to have a distance that overlaps another distance. You know, like you go around the curve more than once. Hell, that happens all the time. You run around the track, you run around the track once, you run around it 10 times. Right? So imagine this. You run around the track for like an hour straight, and somebody tells you, oh, okay, you just ran for 100 meters. You're like, no, I ran for more than that. Or like, no, I only saw you run for 100 meters. I measured the distance around. Is it 100 meters around one full, or is it 400 meters? It's 400. Okay, so you only ran 400 meters. Why? Because, well, whatever the distance is around, right? Quarter mile, if we're being American about this, I guess. because it's four laps for 1 mile, if I'm not mistaken. So they say you only ran for a quarter of a mile. And that's because all they did was they measured the length around 1 lap. They didn't account for the fact that you went around like 20 times, right? So in the case of area, I only need the distance around 1 time. But in terms of arc length, I may need it more than 1 time, less than 1 full loop. It's all sorts of possibilities. So even if I went down to 7, I'm still completing the loop and then some. It wouldn't be until I got down to 6 where I would say, oh, okay, now I'm short. So it's somewhere between 6 and 7 that closes the loop, in which case you'd settle in on pi. All right, so that's an important recognition, because if you don't know that your domain is appropriate, then it's a non-starter, right? Like you could run these calculations, but you're not going to get anything meaningful from it. All right, so in this case, we know 2 pi is good, but the cautionary tale is important. So 0 to 2 pi, 1/2 r squared, whatever your r is. This is my r. 2 plus 4 cosine theta d theta. So in the previous question, it was a nice luxury that you were able to use your calculator. You know, it's like, I could have done it either way, but you know, if I want to be fancy, I guess I could use my calculator. Here, you want to use your calculator, because the only way you're getting this antiderivative is to simplify first. So distribute it out, combine any like terms, multiply through with the 1/2, and then do a trig substitution. Actually, sorry, a trig identity substitution. All right, that can sometimes be harder than just an ordinary trig substitution, because that requires you to know trig identities, like the cosine double angle identities. Right? Because if you're going to take the antiderivative of a cosine squared, you have to know that you can swap that out for a 1 plus cosine 2 theta over 2. How many people remember that from Calc 2? A couple people, right? There's always a few people, right? But the rest of us, like, oh, yeah, I guess I got to review that. Or you pop it in your calculator. All right. This is, I don't know if this is going to work. But Math 9, 0 to 2 pi. Make sure you're in the right mode, for crying out loud. That's what you should be saying to yourself during a test. Just make sure you're in the right mode, for crying out loud. I mean, you could throw some colorful metaphors in there if you want. I don't think I've ever made a mistake without cursing at myself at some point. 2 plus 4 times the cosinus of theta. And then pop in your theta. If you're in polar mode, that's what comes up when you hit X. All right? If you're in polar mode, when you hit X, the theta is going to come up and you're going to be in good shape. All right? So just go back, double check that you didn't type in anything incorrectly. And again, you know, like, people either love this or hate it, but I know some of you are only in this class because I allow stuff like this, and that's fine, because we're going to do some hard math in this class. Don't worry, it'll get harder, but this is not, I mean, this is Calc 2 content. You've already been assessed on it. You got a grade for that course. I don't need to grade you again. All right? So type in your expression. Be careful about it. Make sure you type it in correctly. And hit enter. 37.7-ish. If you want, divide out a pi to see if it can clean up. It does. So this gives us a 12 pi. A very satisfying 12 pi, I might add. I keep hitting the right button expecting, I'm sorry, I keep hitting the wrong button expecting the right thing to happen. Hey, what's that all about? That's not at all what appears on my screen. There it is. Just need a little memory jog there. All right. Yeah, so we'll just focus on areas for now, because again, we're in a groove for that. So the last one I wanted to do today is the area between two graphs. So you have two graphs or two equations, which means that you have kind of a sticky situation when it comes to domains, because sometimes a domain that works for one doesn't work for another. So it may be perfect for the r equals 3. In fact, it is, because we know it is. We did it already. But it may be an overestimate for the r equals the square root of 9 cosine 2 theta. All right, so just give it a quick look in your calculator. So I'll just type it in and then I'll show you on the big screen real quick. So the big drawback when it comes to the calculator is stuff like this. This is desperately trying to graph a lemniscate, a propeller looking graph. So this should be connected.
No, it shouldn't.
Yes, it should.
No, it's undefined at pi over 2, 3 pi over 2.
1 second. Back to this. R can be positive or negative and still get you where you need to go, because you're allowed to aim your R in any particular angular direction. So just because we can dismiss a particular negative R doesn't mean that it's eliminated completely, because we could always cover it with a positive R. All right. So it should be connected on the graph. It fails to do it. And that's a drawback to the graphical technique. It's kind of annoying, but we learn to live with it. The issue when it comes to something like this in dealing with the technique that we're working on is really more pronounced than that, because the method I just showed you, the idea of dialing back your domain until it shows that it's less than a completed graph, that's troublesome. Because if the graph doesn't depict it as a completed continuous graph, or the calculator doesn't depict it as a completed continuous graph, then to begin with, then no matter what we do to the domain, it's not going to fix that. All right, there is something that you could do to the theta step. You make your theta step like minuscule, and it'll come closer to completing the curve, but it'll never actually look perfect. All right, so what do? What we can do here is actually solve and make a determination of where the loop would be closed. All right, because a lemniscate opens and closes at the pole. So what I would do here is take my R equals the square root of 9 cosine 2 theta, set it equal to 0, senior moment. So the graph is going like this, then going through the pole, then back. And so this is the key point, which is 3 units away. All right, so that's the missing unit. That was so weird. So what we're supposed to do, using a technique I like to call the right way, is set your equation equal to 3, because that's where it's supposed to close. And that should, in theory, make a lot more sense. All right, then solve. 9 equals 9 cosine 2 theta. Still need to know some unit-circle trig, or at least be able to finagle a solution to unit-circle trig without knowing unit-circle trig. All right, but it's the same idea. So I need the values in the circle where cosine is equal to 1. All right, so
0 degrees and pi?
Well, pi would give us, yeah, 2 pi is what we want, because pi would give us a -1. 3 pi, yeah, 4 pi, any even multiple of pi, etc.
Don't really want one single.
Right, that's what I'm getting at. So I'm listing them all out, and then solve. 0, pi, 2 pi, etc. So now I need to determine where it's going to hit the pole. All right, so we're looking at where 0, just kind of jot it down here, would be equal to the square root of 9 cosine 2 theta. All right, so 9 cosine 2 theta would be equal to 0 if I square both sides. Divide out the 9, and you get cosine of 2 theta is equal to 0. All right, that's going to happen wherever 2 theta is equal, or 2 theta gives a value where cosine would be equal to 0. So that would be pi over 2, plus or minus, but we'll just stay with the plus for now. 3 pi over 2, 5 pi over 2, etc. In which case I'd be looking at theta being equal to pi over 4, 3 pi over 4, 5 pi over 4, and so on. Since we're looking at a symmetrical figure, I mean, my drawing notwithstanding, all I would need to do is figure out the area contained from the start point to the moment where it hits the pole, because that'll be 1/4 of the entire area. We know that the outer figure, the one that's going to encompass this, is a circle, and get ready for this lovely circle. Oh yeah, look at that. All right, this has a radius of 3. We've already figured that out. All right, so the area here, we did that in the first problem. Area is equal to 9 pi. All right, so if I could just figure out this piece here, then I'll be in good shape. So I know, based on my solutions over here, that the lemniscate starts off at 0, and then it hits the pole for the first time at pi over 4. That is not a highlighter, fun fact for the day. That would be the highlighter, right? Yeah. So I'm going to integrate. That's a little thick. I'll live with it. From 0 to pi over 4. 1/2 r squared. So the r is the square root of 9 cosine 2 theta. D theta. And multiply the result by 4. All right, so I'm just going to run that through the calculator. Math 9, 0 to pi over 4. Pop in the 0.5. I mean, you could actually just square away the radical if you want, and just type in 9 cosine 2 theta. D theta. 2.25, multiply that by 4, and we get an even 9. So that's equal to 9, surprisingly. So the difference, so it's area of the circle minus the area of the lemniscate. Looks like an infinity, but it's not. 9 pi minus 9. And units would be, area units, so square units, but at this point it was left purposely vague, so I wouldn't have to worry about that. All right. The benefit of doing it this way by utilizing symmetry is that if you get any negative areas, and in this case you do, because the part of the video that I deleted and I'm now overwriting is the part where I screwed it up the first time and just went after it like an animal and went for the entire lemniscate and it's zeroed out. All right, so if that happens, it's because you have equal parts positive area and equal parts negative area. And so when you add them all up, it goes to 0. If you look for symmetry, take a part that you know will be positive and then work off of that, then you're much less likely to make the kind of mistake that I did. Well, I suppose. I'm going to go purple for those keeping score at home. So S would be equal to, on the interval of 0 to 2 pi, all right, so I need the R value and I need the R d theta. All right, well, the R d theta is pretty easy. I mean, it's very easy. I could just, let me tuck it in, sneak it in right here. dr d theta be equal to 0. All right, so again, we're looking at the square, I zoomed out significantly, but it's the square root of r squared. So 3 squared plus dr d theta squared, so 0 squared d theta. So that's going to end up being, if we clean it up, just because why not, right? The integral going from 0 to 2 pi. This is immaterial, the 0 squared, it's irrelevant. So the square root of 3 squared is 3 d theta, which would be 3 theta on the interval of 0 to 2 pi, which would amount to, and normally I wouldn't even bother doing it by hand, but it's simple enough. I think it's actually easier to do this by hand than it would be to actually even type it into the calculator. So 3 times 2 pi would give us 6 pi. Oh, there's a little lag now. Minus 3 times 0, which is just going to be 0. So I'm not even going to write that. So our arc length S would be 6 pi. All right. Now, very easy to check. That's why we start off with this example. Because if you're dealing with area, it's pi r squared, which we talked about last time. If you're dealing with arc length around an entire circle, you're talking about a circumference. All right. Now, if I limited it, if I didn't go around the whole way, if I only went to pi, for example, half a circle, or pi over 2 for a quarter of a circle, pi over 4 for an eighth of a circle, something like that, then I have to restrict this. But this is talking about the length around an entire circle. So it's talking about the circumference, which is pi d. All right, radius is 3, diameter must be 6. Pi times 6, 6 pi. All right, so very easy to verify. Now, the second one, a little bit of a different story. All right, so here I'm actually going to show this, the steps to find the derivative, dr d theta. And I should note here that this is the area up here. So dr d theta would be, well, the 2 goes away, so 4 times negative sine of theta, so negative 4 sine theta. All right, so my arc length formula, still going from 0 to 2 pi, we'd be looking at the square root of r, not literally r, what r really is, 2 plus 4 cosine theta squared plus negative 4 sine theta squared d theta. All right, so r squared plus dr d theta squared. So then we clean it up. Maybe. I mean, if you find it to be beneficial to clean it up, then definitely. But maybe at this point you say, I'm going to go to the calculator. And that would be perfectly reasonable. So I'll just do that real quick. And so this is what I offer you. You know, you you don't have to do definite integrals by hand. At least not when you're dealing with functions of a single variable. When we get to multivariable stuff, this is not a multivariable calculator, so there's going to be some exceptions to that rule, but...
Are there multivariable calculators out there?
That is a good question. One that I've never explored the answer to. Because...
You don't know if people cheat.
Yeah, that's the thing. It's like... If I'm not familiar enough with the calculator, then I'm not familiar enough with the way that people can cheat with it. That's what bit me that one summer in Calc 2 with the TI Inspire. That's why we don't allow those. People.
They program the whole thing. Right?
Oh, it's worse than that. They say they're capable of storing PDF files. So they took my entire notes and saved it in there. Like, I'm looking at this person, like, I mean, it's not the most user-friendly screen in the world. So they're like hitting a down button, like really looking at their calculator, but doing it for like 10 minutes straight. I'm like, no way they're tracing a graph. I got to see what's going on over there. And it turned out that they were accessing my notes.
Did they get a 0 from that, or?
Yeah.
That's dedication and shit like that.
Yeah, and I have to say they indirectly got a 0 because
You didn't say they couldn't.
Yeah, so it wasn't clear, but I just made it very not easy for them to pass after that.
Well, it's very obvious that it is cheating.
Yeah.
You download.
It still wasn't as bad as the girl who asked if she could listen to music during a test. I was like, yeah, I like to listen to a little music. It was my YouTube channel. So that was unfortunate.
That sounds just like.
Yeah, it's a good way to go if you can get away with it. It's just I was like, what is that annoying sound coming from those headphones? I was like, damn it. I walked into that. That was my voice. So I popped in the integral. I mean, it's in function mode, so it came up with x's instead of thetas, but nobody's losing any sleep over that. Oh, wow. Oh, no, not wow. Forget it. So it came up with this decimal, and I figured, okay, I'll give it a shot. Maybe it's a multiple of pi in some way. If it is, it's not a clean one. I mean, it might be a multiple of pi in such a way that the multiplier is a radical. If that, I could try that. No, yeah, it's just a disaster. Maybe it's a perfect square or a square root of something, and also a multiple of e. Yeah, nothing. Yeah, it's a disaster. Let me go back to this though, HDMI. All right, so I don't like that lag. So about 26.73. Right, the whole point behind this is that you're using the calculator and it's installed functions to your advantage, to the utmost advantage. There's some other functions that we'll learn about, like ones that we'll program in there. I'm not in the business of making people clear their calculators before tests, just because I'm like, listen, if you need to put in that the derivative of sine is cosine at this stage of the game, by all means, put it in. Like what does that matter? That's not the big deal, And if you want to put in, when we get to the multivariable stuff, if you're going to sit there and type in line after line of definitions related to multivariable calculus, more power to you, because that's going to take you a while. And then to be able to actually sift through it all during a test, it's going to work against you. So I don't even bother regulating that sort of thing.
You probably haven't memorized after you type it all out.
That's usually what happens. I remember that. It's like I started when I would be allowed a note card or something like that for a test. I would start by just writing down formulas that I knew, and then I would immediately crumple up that index card and throw it away. And like, well, I already know those, so why the hell did I waste index card space with that information, because I already know it. So then I start thinking about things that I don't know, which is the problem, because if I don't know it, how do I put it down on a card? And so what do? I grab somebody else's card and say, what do you got down there? Write it down, hope it's all correct. And then you get into a test, you look at it and say, it's cool to have formulas and stuff. I don't know what to do with this, you know? So, studying is an important thing more in this course than anything else, I would say, even more than Calc 2, because it's more fact related. Right? So there's plenty of situations where you're using a skill and demonstrating knowledge of that skill, but oftentimes the sticking points in this course come down to just straight up knowledge of facts. If you know those facts, then you're good to go. If you don't, then you're not, right? So, because most people know what to do once they have those facts. Like I said, the solution for the last problem there, I posted that online. I'll do another area problem so that we could see it live in person, hopefully correctly demonstrated, and then we'll move on to actually taking derivatives of involving polar full stop. So, all right, so we have r equals 3 times the secant of theta, r equals 6 times the cosine of theta. Theta is only going from 0 to pi over 4. All right, so we're keeping it in the first quadrant in terms of the radian measures. What that translates to in terms of coordinates, not necessarily going to be limited to the first quadrant, because you might end up with, let's say, if I plug in pi over 4, I might get a negative r value. If that's the case, that'll put me in the third quadrant.
So when you're graphing this, is it still going to be on the x-axis from 0 to pi over 4?
Is it still going to be on the... So the rotation is going to be in terms of...
No, when you graph it, you're still going to see rotation, but like the measurements, are we going to look at anything past pi over 4 on the x-axis? Or we're just going to ignore that section?
So the pi over 4 won't be on the x-axis.
No. I'm talking about when we graph it.
Oh.
Yeah, no.
Yeah, no.
We actually draw it.
I thought you were talking about like the hand draw.
No.
Which I'm going to sketch out in a second. 0 to pi over 4, and that's it. Nothing
That's
beyond.
it.
Yeah. So graphically, we'll take a look in a second, and you'll see it's pretty nice. But let's actually try to visualize what these two figures might end up being without using the calculator, because sometimes that can be helpful. Especially the first one.
Are you going to record it?
Yeah.
Oh.
Yeah. I get the meter running on here. It just doesn't show up on the big screen. Always a good question. So secant theta is the reciprocal of cosine. If cosine's x over r, then secant is r over x. So you'd have r equals 3r over x. The r's would cancel to a 1 on the left-hand side, and you get x equals 3. All right, so in terms of function type values, so rectangular mode, this would not be a function, but in rectangular form, you're looking at a vertical line, right? So it gives you a sense of what you're up against. Because when you put it in the calculator, it's going to look vertical, but it's going to be a question of, is it truly vertical? If you know it's definitely vertical, then you could rely on that information, all right? We'll come up with some points to create the graph in a second, but to know that it's a vertical relationship is very important, all right? The second equation, and by the way, it was nice and easy to do, so why not, right? So r equals 6x over r. That's a different story, because the r's don't cancel out there, not in a nice way. We'll get r squared equals 6x. And r squared could be replaced with x squared plus y squared. Okay, so making kind of a judgment as to what this is, it's kind of a little iffy at this point. If you were to bring the 6x over, subtract it, leave a little gap to complete the square. And then complete the square, you're going to see what kind of figure this would be in rectangular form. Completing the square just for the x's, what number would I put in the blank there?
9?
It's going to be a 9, yeah. Good old completing the square. Everybody's favorite topic. You know, it's just one of those topics where x minus 3 squared, it comes and it goes. It's like really, really important for a little while. Then it disappears for a while to the point where you're like, why did we learn that? Then it comes roaring back. Then it disappears again, pre-calc. Then it comes roaring back, calc, limits. Then it disappears. Then it comes roaring back in integrals, you know, when you're dealing with the different types, when you're focusing on inverse trig functions and stuff like that. And then here we are again. And so it's always making an appearance in every course that you take. It's kind of crazy when it comes to that. And then when we get into the third dimension, it'll come roaring back again. It's great. So I have videos online how to complete the square. So that's good news. All right. But basically, if the leading coefficient is equal to 1, you're just taking your b value, you're chopping it in half and squaring it. All right. There's more to it than that, but at least this will get you to a point where you understand where this 9 came from. All right. And I have to add it to both sides to make it a balanced equation. But this is clearly, if you know the general form or standard form of a circle, this is a circle equation. Center at 3, 0, and a radius equal to 3. All right. So it's kind of helpful to get a sense of what it is we're up against, because now I can draw this picture. I mean, I'm going to draw it poorly because it's me. I mean, you don't know me very well, but this is one thing you know very well about me at this point. I can't draw. I try. I know. Try not. All right, so so we have x equals 3 here. Have vertical line x equals 3. And then we also have the circle. All right, so then it becomes a question of, all right, that's all well and good. Wonderful news. What part of this am I looking to find the area of? All right, that ends up being the big challenge. All right, so once you kind of puzzle that out, everything's fine. So let's take a look at the calculator real quick. So let me get rid of this. It's bad background. Sometimes it's a matter of preference, but in a lot of cases it's a matter of, I think this is the way to go, so I'm going to try it. And then you try it, and it's not the way to go. All right? The way it's going to turn out is that in polar form, this is probably the more useful one to work with. In rectangular form, the r equals 3 secant theta, we would want to convert that over, all right, because that's a little easier to visualize. All right, so I'm just going to kind of squiggle off here. We're still going to make use of that work, so it wasn't a waste. So r equals 6 cosine theta. So the good question that was brought up before, or the thought that was brought up before, was, if you know the special points, or I'm paraphrasing, but if you know the special points along the graph, do we have to create an entire table of values, or just whatever it takes to get the job done? So that's an oversimplification of what was said, but it's basically like, if you know what the figure's supposed to look like, and you have the special points, then you can just ballpark the structure of the graph. So here, I would need to know the endpoints of my domain, 0 and pi over 4, 0. I got to start deleting some videos because my iPad's getting weighed down here. So if I plug in a 0 here, cosine of 0 is 1, so it becomes a 6. If I plug in a pi over 4, we're looking at radical 2 over 2 times 6. All right? So 6 times radical 2 over 2 would be 3 radical 2. All right? Maybe a decimal approximation's in order. Just for the sake of plotting it. So about 4.3. So if I'm drawing a polar graph, so I'll do, this is my attempt at a polar graph. 1, 2, 3, 4, 5, 6. Yeah, look at that. Good looking graph right there. That's the way we draw it up in the playbook. That would be 6, 0. Then 4.3 steps in the direction of pi over 4. So we're just estimating. 1, 2, 3, 4.3, like right over here. We know it's supposed to be circular. And we know it's supposed to intersect with a line x equals 3. So you can get your little hunk of the pizza. I mean, it's a quarter of a whole pie. I mean, to call it a slice would be ridiculous. Yeah, it's really like Frank Pepe's pizza. It's all misshapen. So, but delicious, of course. But misshapen, along with the Pepe salad. And you go with roasted red peppers on the pizza. So you can't go wrong with that. It's tasty. It's sweet, flavorful, but it also has enough of a spiciness kick to it where you feel like you got what you came for. Right? So it's on Central Ave in the Yonkers area. So anyway, delicious stuff. I like Frank Peppers. They're always pushing their clam pizza. I'm not a clam guy. I mean, I like clams enough, but not on my pizza. So anyway, what I would have to do is figure out the area contained in that region. So one way to do it, I mean, it would be perfectly reasonable if this were not a calculus course to say, well, let me find the area of the whole thing and then chop it into quarters. Right? The problem is it's a calculus course. And so we need to do some calculus. All right, so we'd have to start thinking about if you had an integral to set, to determine our area, what would it really give us? So this is I'll call this the pole. This is the end point of a circle. Here's the beginning of my wedge. So it's looking something like that. All right. When I go to find the area, when I set up the integral related to the circular part. All right, so what I'm going to do is I'm just going to say the integral. It's 1/2 r squared d theta. So 1/2 the r 6 cosine theta. Oh, it's right in front of me. Okay. On the interval of 0 to pi over 4. That would be an integral based on the formula, perfectly acceptable. But you got to think about what that gives you. That's going to give you everything from that outer boundary back to the pole. It's going to give you all this. All right. So what I need to do is get rid of all of this area. Like half of a sideways ice cream cone. So I would have to subtract from it the integral, also from 0 to pi over 4, 1/2 r squared d theta, what was that, 3 secant?
Mm-hmm.
D theta. All right. One thing that's important that you always have to keep in mind, and this goes to that example that we talked about last class, or that we finished up last class with. The reason there was a mistake is because I brain cramped, but more than that, it has to do with the movement from one point to another within the figure. So if there is anything other than a counterclockwise movement, aka a clockwise movement, it's going to bring back a negative area. All right, so sometimes those positive and negative areas can offset. If we're looking for the total area contained within bounds, what I would need is the difference between absolute values of those areas. So one way to handle that would be to figure out each of these areas individually, make sure that they're positive before you do your subtraction. Or another way to do it would be to slap this whole thing with an absolute value bar. You could do that. Or I think the easiest way would be to just look at the figure being graphed. All right, so I'm going to bring it in a little bit. Instead of going from -10 to 10, I'm going to go from 0 to 6. And instead of going from -10 to 10, I'm going to go from 0 to, because all I need is, well, I'll go from 0 to 6 again. All right, and then we just want to watch it being graphed. And if you want to watch it, if you want to slow down the process, change your theta step to something small. All right, so make it 0.01. You don't actually have to see the entire graph being generated. You just have to see what the movement is looking like. As long as both parts are going in counterclockwise form, you're going to be in good shape. Recommendation, I think I've made this before. If not, I apologize. In your mode, my calculator gets reset. Actually, I don't think it gets reset. I think it gets changed by somebody like every day to what they think the best form, the best format is, and it's not this. Sequential is fine, but simultaneous mode is where you want to be. All right, because that allows all of your graphs to graph at the same time rather than waiting for one to finish before the other one starts. Especially if one goes off to some kind of infinity and there's asymptotes everywhere, it can take a while. All right, so I'm going to hit graph and then just observe what's going on. Counterclockwise, if it's, it's vertical, so it's going upward, but upward is still following the idea of counterclockwise. All right, if it were going downward, it would be clockwise. All right, so it would have to start somewhere and then work in a downward direction. All right, so both parts are going counterclockwise, so that tells me I could just pop in this whole set of integrals. So math 9, 0 to pi over 4. Point 5, 6 times the cosine of theta squared d theta. You could put it all in one integral because your bounds of integration are the same, but I'm doing it separately. Math 9 again. I just got in the habit of doing it this way over the years because oftentimes, not always, but often enough, it would be something like find the area between them, but then maybe like find the area contained within just one of them or the other of them. So finding them individually always seemed to make sense. All right, so assuming I typed that in correctly, that's the big crapshoot. I'll double check my mode again. You get that. Just quick check to see if it's a multiple of pi. It is. So math frac that. I know it's, well, I was going to say I know it's 5/4, so I'm glad I didn't just go with that because it's 9/4. So 9 pi over 4 is what we're looking at. All right, so If you assume it's some multiple of pi, you can check it out that way. Not a requirement, unless it's a requirement. So that's the thing you got to keep in mind. The directions on a test will indicate that clearly. It'll say answer needs to be in simplest form in terms of pi, or it'll say round your answer to the nearest tenth.
But why does it matter if it's counterclockwise or not?
Because a counterclockwise movement will give you a positive angle, which would create a positive area. Because really, every 1/2 r squared d theta, every one of those is the area of a little tiny sliver of the region that you're looking to find the area of. So if it's a positive movement, that'll return a positive angle. If it's going in a clockwise direction, that's going to give you a negative movement and give you a negative area. All right? And sometimes those positive, it's just like in Calc 1, where if the function was above the axis, you got a positive area. If it was below the axis, you got a negative area. And sometimes they offset. So if we're looking for total area, that would be a problem. And that's the case here.
Okay, that's why you told us to put it in the calculator. It shows like whether it's going clockwise.
Exactly, it shows the movement. And that's really where I ran into trouble last time with the Spider-Man question. It's just because the calculator couldn't handle the lemniscate, so I couldn't get a good reading, a good beat on what the movements were, because it started off counterclockwise, then it switched over to clockwise, but it didn't really show up like that in the calculator. So it wasn't until I started plotting points out on my own that I was like, that's where everything went wrong. So, question?
No, so when we put in 6 cosine theta from 0 to pi over 4, I noticed that if it wasn't for the 3 secant theta, we would have gotten the area wrong no matter what. Like, how would we have known what amount of area to subtract? We would get an idea that, yeah, that one section of what you drew there, we'd have to subtract, but it's because you gave that to us. It's because you gave us the secant theta. If we just put in 6 cosine theta,
Then it would give you the whole slice of pizza.
no, it would just have given that like one little curve.
It would have given this whole shebang.
No. the right side. No, I mean like when we graph it.
Well, if it's
Oh,
Because it's from like 0 to pi over 4. I'm saying,
I thought you were talking about area.
No. Well,
Because the integral is still going to return the area contained
Yeah,
between that sliver and the pole.
exactly. That's
Right.
what the area would have given us. But I'm saying that if it wasn't, if we hadn't been given 3 secant theta,
It would be-
we wouldn't have known that it's specifically 3 secant theta
Right.
we have to take out.
So you'd have to go all the way.
And then how would we know?
Well, that would be the question then.
yeah.
We would just say like this sliver right here.
Yeah, I mean, it would really just be a matter of you're finding the area contained between this arc and the pole.
Oh, then that okay. You wouldn't ask us something.
No, I mean it's like that would be the question.
Okay.
Yeah. So it wouldn't be an area between anything in that case, right? And in this case, what do we have here? We had a radius of 3. So area of the whole circle would be, it's pi r squared, so it would be 9 pi. Break it up into quarters, you get 9 pi over 4. So you could visualize what's going on by getting into function form. I keep saying function form, rectangular form, because it's not always functions. And that gives you a sense of what you're up against, but it isn't until you do the calculus that you earn calculus credit here.
Very similar to, like, let's say we had to find the inner loop or like whatever outside the inner loop of a limit is on. It'd be very similar to doing this, correct?
Right,
Okay.
right, exactly.
Do you feel like
It's gonna be something like, hold on, I'm gonna draw it. I can't, well, we know I can't draw, so I don't have to say it over and over again. All right, something like that. So we need basically the bounds of that inner loop. And so it starts off, you go into the loop through the pole, and then you come out of the loop through the pole. So we'll figure out where it's at the pole. So 0 equals 2 minus 3 sine theta. All right, now let me just double check and make sure that I have a sense of how this graph is being graphed. Right, okay, so it's coming around and then coming through and over and back.
Right.
Okay, so all the way through, it's counterclockwise, so we're not going to have any issues with the integration process. All right, so this is the pole. So we're looking at sine of theta would be equal to 2/3. All right, so not a nice clean unit circle number. That stinks, but we'll live with it. So theta is going to be an approximate form, so we'll have to deal with that. So we're looking at about 0.73. All right, so
Yep.
let me just do a quick value on that, 0.73.
Yeah, I just divided sine of 2/3, 0.7297.
Right, okay.
So it's 0.7.
So then we just need another location in which the sine function would also have a ratio of 2/3. So that's the part where it gets weird. So ASTC tells us sine is a positive ratio in the first and second quadrant. Right, so that should be a 0.73 in the second quadrant, which would be pi minus 0.73, which is we did approximation on the first one, so we might as well. So that's going to be about 2.4.
Yep.
And I just checked, and it does go to the poles, so we're in good shape there. All right, so if we're looking for the area here, again, it's 1/2 r squared d theta. So our r is 2 minus 3 sine theta. Our bounds would be going from 0.73 to 2.4. Now, if we had to do this out by hand, it would involve some identity substitutions, but we don't have to worry about that because I'm a stickler for some things. This is not one of them. So pop it right into the old quackulator here. Sine of theta, close it up. Yeah, 0.44-ish, 441. So I'll double check me, you double check you. Let's see, 2 minus 3. That looks fine. Got my 0.5 in there. Checking.
Oh,
Found it?
I forgot to square it.
Ah, there you go. All right, so 0.441 would be the area. And yeah, I mean, scale-wise, it seems reasonable. And it's a small loop, so it should be a small number, I guess. Not going to bother trying to go to an exact form because I'm working with estimates on the bounds, so that's perfectly fine with that. There you go. Well, this graph is just fun to look at, but you may notice I have a dy dx here. So a polar graph, right? So it's r is a function of theta, right? So if that's the case, then you have r's and thetas embedded in an equation, and so how do we get from r's and thetas to x's and y's? All right, there's two ways to handle it. One would be to do a conversion right off the bat. And we talked about this previously, definitely. So if you know that x is equal to r times the cosine of theta, and y is equal to r times the sine of theta, basically a parametric equation where the parameter is the angle as opposed to being time. All right, so I can use this information to come up with a dy dx. And you could do it, like I said, one of two ways. Do a conversion early on, change polar into rectangular, and then take the derivative the way you would in Calc 1, or we can invent some rules right now where we're taking the derivative of these relationships and going from there. So it's just a question of dx d theta or dx dr. The answer is it doesn't matter. All right. So, and the reason I can say that is because essentially I'm going to be taking dy d something here, getting that result, and then dividing it by dx d something in order to get dy dx. All right. So what I would do in this case is take a look at the function that I'm trying to differentiate, or the set of equations that I'm trying to differentiate, and just think about which would be easier to work with. I think clearly the r would be easier to work with. We have a function of two variables, r and theta. So this is an implicit situation. So it's a question of, do I want dr d theta or do I want d theta dr? Right? Either way, it's not going to make a difference. So what we're going to do, is because it doesn't make a difference, is take the derivative with respect to r. And I'll show you what it looks like the other way in a minute. All right, so if I do dx dr, it would be first function. It's implicit, so first times the derivative of the second. It's a product rule situation. Plus the second function. Oh, sorry. It's implicit. I said it like 3 times. D theta dr. Plus the second function, cosine theta, times the derivative of the first, which would be, well, dr, which is just a 1. All right, so 1. All right. So that's one possibility. Or I could say dx d theta. So I'll do the same process again, just this time with the d theta as my independent variable. So first times the derivative of the second, still the same idea. So r times the derivative of cosine is still negative sine. But it's with respect to theta, so I don't need a dr d theta dr d anything, because it would be d theta, which would go to 1. All right. Plus the second function, which is cosine of theta, times the derivative of the first, which would be dr d theta. All right, so then we're really just kind of taking stock of the situation, saying, all right, well, which do we like more? Right? Which can I make use of more? I can clean it up a smidge. I can clean them both up. I'll tuck a little or in there, because we're not going to need them both. We'll make a choice, and then that'll be our rule of thumb. All right? So it's just a question of which do we like more. Now, do we like? You know, I speak like that sometimes. It's not always a matter of what we like or what we don't like. It's a question of what fits what fits the available information. All right? So what available information. We'll just take a quick look at, sneak a peek at an example here. So, first one says, write the equation of a tangent line to r equals 1 plus the sine of theta. So, I would ask you, is it going to be easier to find from this equation here d theta dr or dr d theta? If I were to take the derivative of this, what would the left-hand side of it be? dr d theta, right? Right. So if I needed d theta dr, I could still work with this first equation. I can get a d theta dr. I would have to take the derivative of this and then flip it over. All right. Doable, but it seems like unnecessary extra work. So if that's the case, then we can kind of lock in on this one being our dx d theta. All right. Or at least the preferred one. So why do I go over the other kind? Well, what if you're given a function, a polar equation that's defined as theta equals something in terms of r? If that's the case, you might want to go with the other option. Right? So that's just something to think about. Now, dy d theta. So, since we decided to go with dx d theta, there's no point in getting into dy dr. We'll go right to dy d theta. So first times the derivative of the second. So first would be r. The second would be sine theta. So r times cosine theta plus second times the derivative of the first, so sine theta times dr d theta. So this one looks a little cleaner. R cosine theta plus sine theta dr d theta. All right. Now, this is combining the concepts of polar equations and parametric equations. So dy dx is the dy d theta divided by d theta, dx d theta. So we're looking at r cosine theta plus sine theta dr d theta and then the denominator would be negative r sine theta plus cosine theta dr d theta. And really, there's no simplifying this any further. That's your formula. I believe I'm going to go down this road again. I believe I mentioned at some point that I like to put a derivation on a test. I always put one derivation question where you're expected to invent a formula like we do in class. We did it with arc length for parametrics, and we just did it for the derivative dy dx related to polar equations. All right, so a question on the test could be, and when I'll post up a revised review sheet, but what I usually do is I give you the set of possibilities for a derivation. I'll say it could be this is what the solution would look like, could be that, this is what the solution would look like, and whatever. So I'll give you like 3, you prepare for all 3 of them, and only one of them will be on the test. All right, but it would be something like x equals r cosine theta, y equals r sine theta, what is dy dx? So it's running through this process, but this process, even though it seems Calc 3-ish, it's all Calc 1. Right? It's implicit differentiation. All right, so now there's challenges with that because Calc 1 was like a year ago or more in some cases, so it's like, oh, you should have learned it then. Well, woulda, coulda, shoulda. Like,
That one probably too.
so The equation of a tangent line. So that's an application of it. Write the equation of a tangent line to r equals 1 plus sine theta, where theta is equal to pi over 3. All right, well, personally, I like to get all my busy work out of the way immediately. All right, so I have my formula here. It's got a lot of ingredients, right? But I essentially need dy dx when theta is equal to pi over 3. All right, so dy dx when theta is equal to pi over 3. Now, I can write out that entire formula and then do some substitutions, but before I do that, because I really don't want to do that, I would figure out what r of pi over 3 is, because all of this is happening at pi over 3. So I'd figure out r of pi over 3, because if all I'm going to do is substitute in a 1 plus sine of theta for r, and then replace the theta with a pi over 3, why not just figure out the r of pi over 3 right off the bat? Then I'd figure out the cosine and sine of pi over 3. And then I would need the derivative at pi over 3, dr d theta. So I would make a note, dr d theta is equal, first off, to cosine of theta. But then I would say dr d theta at theta equals pi over 3. And just figure out all these bad boys right off the bat, and then do my plugging and chugging. The notation here, you may not like it. You may feel like it's unnecessary. I did. I'm really just trying to emphasize the notation now so that it's not as shocking when we get to the multivariable stuff. The idea is that when you deal with multivariable calculus, the notation becomes incredibly important. So if you go from never using the right notation to the point where you're so unfamiliar with it that it's like, whoa, what does this mean? When we do it in multivariable all the time, you're going to be completely lost. All right. So all this is telling us, I mean, the vertical line just means such that, or given. So I want dy dx given that theta is equal to pi over 3. So dr d theta given that theta is equal to pi over 3. All right. So if I'm plugging in a pi over 3 for the sine of theta, or for theta in the sine function, unit circle, that's going to be 1 plus sine of pi over 3 is radical 3 over 2. All right, cosine of pi over 3, that's the nice one. That's 1/2. Sine of pi over 3 again is radical 3 over 2. And then, since the derivative of my r equation, my polar equation, was cosine, it's again cosine at pi over 3, which is going to be 1/2. Those are the ingredients for the slope of my tangent line. So I have my formula. R, well, it's not as nice as it could be, but 1 plus root 3 over 2. Cosine theta, 1/2. Plus sine of theta, yeah, sine of theta is next, radical 3 over 2. Times dr d theta, which is 1/2. Denominator negative r. So negative 1 plus root 3 over 2. Times the sine of theta, root 3 over 2. Plus the cosine of theta, which is 1/2. And the derivative at pi over 3 would also be 1/2. All right, so all of this stuff together is going to give us a juicy derivative. Just for the sake of sanity, or your own, everybody's, I guess. If you were to carry out some of these calculations, you'd see that the denominators across the board would be 4, right? Because at least, except for this one here. So if we were to multiply through with a 4, that would clear out all of our denominators. Okay, so that would give me 4 plus radical 3 plus another radical 3 over, then we'd have, well, the next one's not quite as nice, negative so negative 4, then minus 3 plus 1. Nice. Just making sure. Just making sure. Because it would be, before we multiply it through with the 4, it would be negative root 3. Oh, root 3 over 2. Okay, yeah, so that first one's got to change. So not nice. So negative 4 root 3. Because prior to multiplying by 4, it would be radical 3. It would be 2 radical 3, right? Radical 3 over 2 times 1 is radical 3 over 2, yes? Mm-hmm. Then multiply that by 4, that would become 2. 2 radical 3, okay. So ideally, I'd like to find any mistakes before I go home and have to do an entire lesson again. Yeah. So 4 plus 2 radical 3 up top. And then negative 2 radical 3 minus 2. This is one of those where I don't even want to check it on the calculator. Because if I do, I'll find out that I made a mistake. And then that'll affect my peace of mind. All the coefficients are even though, so let's do that. 2 plus radical 3 over negative radical 3 minus 1. Oofa. All right. So now that we've done all that, I'll go back and find the other mistake. Yeah, because 1/2 times the 1 would be 1/2, right? Then times the 4, that would make that a 2. So 2 plus 2 radical 3. 2 plus radical 3. Yeah, should have been 2 up top. All right, so then negative 1. Do a quick double check-a-rooski of that on the calculator.
It's negative 1.
It is? Okay.
I plugged it in the original one, and it came out to be negative 1, so you're good.
All right. So we have our derivative. I mean, it took me a little longer. Bless you.
Bless you.
Bless you. They are asking for the equation of the tangent line, though. All right, so that's something that we would have to address. Can't just not do it. All right, so the equation of a tangent line, y equals m times x minus x sub 1 plus y sub 1. Well, we have the m part. The issue that would arise here is that we don't really have anything else. All right, so we need an x1 and a y1. So x is equal to r times the cosine of theta. And the r value, the good news is we've already figured that out. This is all happening at pi over 3. So actually, let me let me note that in there. X sub 1, no, I'm sorry, X sub 1. X such that theta is equal to pi over 3 would be r cosine theta, again, such that theta is pi over 3. So then we're just going to go back, and this is why you don't need to go that far. That's why I do all this stuff on the side here, because I have this information. I know it's a 1 plus root 3 over 2, and I need the cosine, which is 1/2. All right, so 1 plus root 3 over 2. And from that, we would clean it up, ideally using correct mathematics. 1/2 plus root 3 over 4. I guess I don't need this extra equal sign up here. Well, it's stuck there now. All right. So then r sine theta would be the other part. You need the y value. Pi over 3, can't just change the angle. My angle looked a little big. I'm changing it. Poor quality pi over 3. All right, so this would be 1 plus the square root of 3 over 2 times root 3 over 2, which would be root 3 over 2 plus 3/4. So we have the slope, and we have the 2 points, or we have the coordinate, all right, but in its exact form. So our tangent line be y equals -1 times x minus 1/2 plus root 3 over 4 plus root 3 over 2 plus 3/4. All right, so that ends up being the equation of our tangent line. It's not pretty, but it's exact, and exact is what we need. All right, so. Well, I mean, we would prefer pretty and exact, but this is the best that we can do when not dealing with overly simplistic cases. Right? That's the thing with polar equations, is that if I make them too simple, then it starts questioning the need for the calculus to begin with. If I were to give you a circle and then tell you find locations where there's horizontal and vertical tangents, you don't need calculus for that. You just need a ruler and eyes. Right? But when you get into like a limacon, the calculations can get a little crazy, but the best you can do by eyeballing it is like, well, I think there's one there, but you wouldn't even be able to come up with a reasonable estimation of what that, what the location would be, all right, without doing the calculus. So it really is, for this particular concept, I'd say it's feast or famine, because it goes from like, this is so easy to the point where I don't need calculus to, all right, the cases where we do need calculus, this is a nightmare. Don't they have like a middle of the road type of example? And the answer to that is no, not really. And so how do we handle that? Well, I give you an omit on the test. That's how we handle that. All right, so, but you look at a problem like this and you're like, wait, so is this an easy one or is this a hard one? I would say that this is it's just one. You know, like, I mean, look at it's a simple-ish polar equation. 1 plus sine of theta. That's not an outrageous equation to work with. But then look what that led to. There's kind of like an exponential relationship between the type of equation and the amount of work that you need to show in order to get the answer. All right, so, and also depending on what you need to do with it. The good news is for number 2, which is the one I'm going to leave for you to try on your own, like a lot of the work is already kind of handled, like derivatives and things like that. So that's going to be a fun problem for you to work on. But yeah, it's one of those like, I was planning on omitting one of those derivations. No. Derivations, you know what the problems are going to be in advance. You don't want to omit those. Those are your gimmies.
Same points.
Yeah. It's the one where, like, personally, I've seen problems on tests, and I sometimes put them on my own on purpose, where it's like any student would look at it and be like, I know how to do this. I also know it's going to take me the next 45 minutes to do it. With that in mind, that is my strategic omit, because I don't want to spend 45 minutes on a problem that I know how to do. Right? I save it, you know, I save my omits for that type of question. The thought-provoking questions, those are the ones that once you do the thinking, you can usually crank it out pretty quickly. But something along these lines, it takes a little while to do. So save it for the end and just write OMIT on it. And just for clarification purposes, because it has come up in the past that not everybody knows what omit means, and this is not meant to sound like a snot rag or anything like that. It's a question that you're allowed to skip and still get credit for on a test. I don't know if that's actually the definition for it, but that's how I define it. So you can skip over it, but then I give you credit. This is the part where I'm cool. So I give you the credit. So if it's a 5-point question, I give you those 5 points. So as opposed, and the only reason I ever started doing that is because I didn't like answering the question, hey, can we do the omit for like extra credit? I'm like, no, I gave you the omit so I have less to grade. That's why I did it. If you start doing it, then I have more to grade. That's defeating the purpose. So you get the points. You have the free 5 points for that question. All right, so it's a nice little, pretty exciting. All right, so, but it's good if you don't have any experience with vectors. This is good because I teach it from the ground up. All right, if you have a lot of experience with vectors, well, it's good and bad. It's good because we do it a little bit differently than you might have done it in linear algebra or even like an engineering course. But there's enough similarity where you're going to be like, I know this already, I know this already, I know this already. But you just got to stay with me because you'll get to a point where you don't know this already and you'll need to kind of flesh it out. The difference between linear algebra and vectors in this course is it starts off immediately. It's the notation, right? Instead of using the square brackets and vertically orienting our vector, we use these triangular brackets, although it doesn't look very triangular here. Right, so right off the bat, it's a significantly different way of thinking, although the operations are going to be very similar. All right, so let's talk about what a vector would look like, or at least initially. So sketch a vector in a plane from initial point p11, right? So just plotting points to 4, 5. So 1, 1 to 4, 5. So rough sketch. So here's 1, 1. Call that point P, 2, 3, 4, and then 2, 3, 4, 5. All right. It probably could have made more use of my available space here, or more effective use of it, but I didn't, and so here we are. All right, so I still have a line draw tool that has not changed. The only thing that changes is my ability to actually use it. All right, so this is a vector in space. Vector in space. just a variation on a movie quote that really can't say in class, although it's fun. I think I heard. So what we have here is a directional relationship. It's always from one point to another. What we want to do is anchor the starting point of our vector at the origin. All right, so that's really what's going to end up happening, is at any 2 points, we're going to have vectors that, or a vector that symbolizes the direction from one, and magnitude from one point to the other, but we want to anchor it at the origin. All right, so this would pop down to 0, 0. So my P prime, I'll call that P prime, because any transformed point, the image we denote with a prime symbol, which is just my way of trying to make this as confusing as possible, because as you know, prime also means derivative. But unfortunately, and I'm just kidding about trying to make it confusing, unfortunately, the prime is used for both derivatives and also images in a transformation. All right, it's just an unfortunate decision that somebody made.
You could just do the zero vector.
What's that?
You could just do the zero vector.
I could, but I wanted to show that that was where P was going. So I moved the point P down 1 and to the left 1, so I'll do the same thing with Q. So down 1 and left 1, so I'm just going to put it roughly around here, so that's my Q prime. And it's supposed to be parallel, so I already screwed that up. We're getting to the point where you might just have to believe me about that.
Wait, if you move Q down 1, 1,
It's
should I
supposed
just
to be
move
the
it
same.
Yeah, it's supposed to be on the same line. Yeah, the Q at 4.
Oh, did I just... Oh, I threw myself off with my own inability to draw.
The freehand graph.
The freehand graph strikes again. For the first time. No, actually ever. Always. Well, I do appreciate you not letting me attempt that 37 more times before letting me know. That's always a good thing. All right, so the vector that's anchored at the origin is defined by the endpoint. All right, and that endpoint, if we dial it back, originally it was 4, 5. Dial it back 1, or down 1 and back 1. Instead of 4, 5, it'll be 3, 4. So then that becomes, in vector notation, the triangular brackets 3, 4. All right. The benefit of writing it like this, it might seem not necessarily the most useful thing in the world, but hopefully it's obvious that we just went from defining the vector by 2 endpoints to defining it by a single endpoint. If we know that one of them is the origin, or the zero vector in this case, then you have a way of defining the direction and then ultimately the magnitude when we get to that of the vector just by knowing the endpoint. All right. So if it's anchored at the origin, all that works out. All right. So a vector in general is really just a line segment indicating the magnitude and direction of something, maybe in motion, or a force applied to a particular object. All right. So magnitude and direction is really the key words there. All right, so let me just throw a little underline on those bad boys. A little highlighter action. Okay, it looks like I scribbled it all out, but whatever. All right. The A vector with initial point 0, 0, terminal point x, y can be written in component form. What I can see on my iPad and what you can see is always going to be an issue for me, as x comma y. All right, so we're looking at the component form of the vector. The x and y values of that vector are known as the scalars. All right, so anything that represents a linear distance is going to be a scalar. All right, so if you're given 2 points, you can come up with the vector in component form without doing all this stuff. Really all we're doing is finding the difference between the corresponding x values and the difference between the corresponding y values. So vector v, in this case, would be 1 minus negative 2 and 2 minus negative 2. So 1 plus 2 is 3. 2 plus 2 is 4. All right. Order matters because order of subtraction will define direction, right? So it's terminal minus whatever your initial is, all right? Because if you did it the other way around, it would still be anchored at the origin, but it would be pointing in the wrong direction, right? So very important that it's terminal minus the initial. But that's pretty common for just about everything that you do. It's usually the initial being subtracted from something later on down the line, VF minus VO, or VI, depending on what textbook you're looking at. So that part should be easy enough. Vectors are equivalent if they have the same magnitude and direction. Right? So I can draw a bunch of different vectors in space that in such a way that when I pin them down, they all give me the same vector in component form. Right? Here's an example right off the bat, because I started off in that intro example with 1, 1, and 4, 5, and that gave me a vector 3, 4. But then I used negative 2, and 1, 2, which would be something like here. I'd have a point down in the negative quadrant here, and then 1, 2 would be somewhere over here. When I put it in component form, it would still give me 3, 4. Right? So it's the same vector. It's just maybe earlier in a process. It's kind of hard to really understand until you have some context associated with it. But there are plenty of ways in which vectors can be the same. If you define the downward force on an object as a vector, okay, so are you telling me that there's only one way that you can apply a downward force of, let's say, 50 pounds? So there's only one human that can weigh 50 pounds, right? So no, that's not how it works. There's plenty of things that could weigh 50 pounds, right? So that's the idea there. Some properties of vectors. I think some of them are obvious. For addition and subtraction, you're talking about just adding the corresponding components. So, we're denoting here with a sub 1, a sub 2 to represent vector A, b sub 1, b sub 2 to represent vector B. You're just adding the x values of each vector together and then the y values of each vector. Subtraction works the same way. Scalar multiplication, that's a dilation if you're thinking in terms of transformations. Right? So if you double the coordinates, you're going to double its distance away from the origin. Right? And that'll have impact on the distance overall, mathematically. Right? But there are some other properties that aren't necessarily obvious. But one of the cool applications of scalar multiplication, vector addition. Huh, look at that. Almost skipped over an example. So this is just practicing the operations, but I think that's something that you can handle, so I'm going to put a little star on that. The cool application of vector addition is that it can take the place of, if you remember the law of cosines, maybe it's something that you prefer to forget. It's good news, because you don't have to use it. Vector addition allows you to do what the law of cosines would do in terms of finding sides and angles in a parallelogram without using the law of cosines. All right, so that's a little added bonus there. But if you like the law of cosines, that might be a problem. All right, so vector addition graphically, very simple. And I don't say that about a lot of things, so I'm going to trace over that line. Now, there's part of this where you're going to say simple for you. And that's only because I have the technology. Okay, maybe I don't. This one I'm going to have to freehand. Oh, it's kind of already freehand, but I'll just get a better one. All right. So, undo. I need my little hand icon here. Yeah, there we go. I'm going to do a little bit of that. And then a little bit of that. Yeah, and again, like I said, easy for me to say. All you're doing is creating congruent opposite sides. So if I had a straight edge, if I were doing this on paper, I haven't written on paper in ages. I don't like paper anymore. All you're doing is just matching up the length of the side. So if you have the edge of a piece of paper, just make a little tick mark to represent the length of the side, and then slide over, maintaining the parallel relationship until you get to the other side, and then just mark off that distance. And then do the same thing. I don't have a folder long enough, but do the same thing. I could zoom in, I guess. On this side, get the whole distance. Maybe I will. Get the whole distance. Get the whole distance. And then swing it on up here and create your parallelogram that way. Most people are fine just doing a rough estimate. Your question would be, am I fine with that also? If you do it on the test, of course. I don't need a work of art. I'm not a hypocrite.
I need to bust out the protractors.
Protractors, compasses.
By the time you finish, the test is over.
Yeah, exactly. Like you've done like the one problem.
Omit the rest of the test.
Oh yeah. It's like a disaster. You know, I'm not even going to bother with the line draw tool on this one because it's just shot. It's trying to like fit me in a particular slot here and it's not working out well. All right, so like that, essentially, without the shaky line drawn. All right, so that is U plus V. Now, if I need the actual component form of that vector, I need this coordinate over here. All right, well, let's kind of wrangle out that information. So drop an altitude here. Vector U has components 2 and 3, which means it's a horizontal movement of 2 and a vertical movement of 3 to get you from the origin to that location. So 2 and 3. So I can do the same exact movement from the end of vector V, which is at 4, 1. So I'll just mark up this part of it also. That's not going to look nice. I'm going to go orange. I know, it's shocking. So this is 4 and 1. All right, so all I need to do is from point B, which is the end of vector V, I know I covered it up, I'm going to go an additional 2 units in the x direction and 3 units in the y direction. All right, so we're looking at And so that would make this coordinate up here. And so I'm just looking at the coordinates, not the vector itself, the component form, which, I mean, they're going to go hand in hand. But if I started off 4 and I'm going an additional 2, I'm now at 6. If I started up 1 and went an additional 3, I'm now at 4. All right, so that's our graphical representation leading us to the vector 6, 4. When I show you how to find magnitudes, then you'll see that really it's just Pythagorean theorem all over the place, because the magnitude formula is how you'd find your distances.
Professor,
Hmm.
were you cutting the x values in half for a reason?
Did we cut the x values in half? I cut the x values in half.
I'm looking at the graph, like, and they're all marked, like each like one.
According to the graph, it's
Oh,
on
it's
your
moving
scale.
by like a half point now. Full point.
Oh yeah, I couldn't figure out how to
Scale.
set up the scale on GeoGebra to make it look the way I wanted to, but yeah, they went by half units.
Oh, they did. Huh?
Yeah. Those people. Alright, so once we learn how to find the magnitude of a vector, you're going to see that coming up with these distances, really not complicated at all. Alright, we could even figure out angles that separate them, all without using the law of cosines. Alright. Very user-friendly stuff. Now, these are kind of fun examples. They don't really, I don't know if they lend themselves too much to a test or anything, but all you're doing is you're creating for A, you're creating a vector that's 3 times the length of the one that's given. So a little bit of measurement goes a long way. Vector addition and scalar multiples and things like that. This is the kind of problem that I prefer that you try to wrestle around with first before I do it all for you, because it's really tied together with this concept. All right, but it doesn't seem like it would be. But I want you to try to think about it a little bit on your own first before we dive into it together next class. Magnitude. Now, if we think of the magnitude of a vector as the length of the side, or the length of the vector itself, then a Pythagorean relationship should kind of like scream at you. You know, because when I drop this altitude here and called it 3, I have 2 legs of a right triangle, a leg of 2, a leg of 3. If I wanted to find the value of u, if u is the length of a side, then I would just use the Pythagorean theorem. All right, the notation can be a little funky though, because u is a vector. So a vector is not a scalar quantity. A magnitude is a scalar quantity. That's an actual distance. All right, so u could never be equal to, in this case it would be what, the square root of 13? It would never be u equals that. It would be double barred bracket around u equal to the square root of 13. So in terms of the notation, acceptable alternative use the absolute value brackets, right? Because magnitude is really talking about the value of the vector, and it should be an absolute relationship because you're taking the square root of positive numbers, so it's going to be positive anyway. So they just usually use the double brackets to distinguish cases where you're using an ordinary absolute value function and you're using the vector magnitude approach, right? So how can we just use this? Well, they're interchangeable essentially as long as you don't get confused about which is which. That's the only reason why this exists, because people will get confused. Like if you're taking a magnitude of something that has an absolute value in it, then what's the, like what are you supposed to do there? The good news is we're hardly ever going to be dealing with strictly an absolute value function in this course, so we can just go with this notation, right? So I tend to go with the double when I'm doing it in class, just because I feel cool doing it, but single absolute values are fine also.
When do you put the arrow on top of the letter versus just having the letter there?
You're supposed to do that every single time you're denoting a vector. I'm never going to do it. I just can't do that.
Oh.
It sucks. Because it's like you go through a problem, and then now I got to go back and put a little arrow thing on top of every U. It like drains my life force out of me every time I have to do it. I had to do that when I was a student, and I promised myself I'd never make the students do it. Like, so what I do is, at least in type form, I try, and you can see in many cases I failed. I try to use an italicized, bold-faced letter, U or V, to represent a vector, because that's also an acceptable way of representing a vector. It's just, I also forget to do that too. So essentially, you're relying on this notation to tell you when it's not an actual vector. These are indicating that it's a magnitude. If you don't see those brackets around it, that's your indicator that you're probably dealing with a vector in component form. All right, which are usually pretty easy to spot, because generally they say things like it's vector V. You know, like in example A here. Find the magnitude. All right, so if I'm looking for the magnitude of V, it would be the square root of -6 squared plus -8 squared. Yeah, you're going to get a clean 10 out of that. So 5 times the magnitude of V, 5 times 10. All right. It's the third one, part C, where we're actually going to kind of discover a relationship. And it's pretty cool. So we're asked to find the magnitude of 5V. So let's figure out what 5V is first. It's a scalar operation. That's the same as 5 times -6, -8, which would be -30, -40. If I'm looking for the magnitude of 5V, I'm looking for the magnitude of -30, -40. And it's Pythagorean again. I mean, it's really just a Pythagorean theorem. So we're looking at 900 plus 1600. So actually, let me just write 2500, which gives us a 50. All right, so the relationship that we get from this is a scalar relationship or a scalar multiple associated with the vector magnitude. All right, so from this, we discover a rule, and that is that k times the magnitude of V is equal to the magnitude of kV, where k is a scalar. All right, now the terminology, I mean, it's a little bit of an adjustment in the early goings if you're not familiar with it. Vectors, we're starting to get a sense of what those are. The term scalar, we'll throw those in from time to time. All a scalar is, if you really want to oversimplify it just to have a working definition, it's just a number. Just some kind of number that you're multiplying by.
Just the K's.
Doesn't have direction.
Doesn't have direction, it's just a particular length or a multiplier, a constant multiple of a function. All right, so if in that case, it should be a little easier. So take the k and make it a 2 or 20, but you wouldn't make it another vector. Vector multiplication is something completely different. So if I'm multiplying 2 vectors, there's a couple of ways I can do it. We could do it with something called a dot product, or we could do it with another approach known as the cross product, something that we'll talk about next time. All right. So there's some more properties here, and I'm just going to put a star on this example here because I think, well, I mean, I know it's the kind of example where I've gone over it before in classes, and it's not, it doesn't land. It doesn't land unless the students have considered the problem first. Like, I'll go through it and you'll be like, oh, cool, congratulations, you can solve the problem. Like, no, I need you to solve the problem. So try it on your own first. Do it on separate paper if you don't like destroying your notes. But this is something that's important. So we're going to talk about that in next class. But before we go, the very last concept, which will only take a couple minutes, I know we're all looking at the clock. And again, I'm not going to always keep us so late. It's just in this time of year, because I don't know how snow is going to impact things. I got burned big time last year. Like, this topic, we didn't get to until like mid-March because of all the snow. We lost like four classes due to snow, and then I was sick one time. So it was a disaster. So, I mean, maybe not from the student standpoint. They were like, oh, cool, half the course.
Nah, that was miserable. Because, like, I had Calc 1 a year ago when that was happening. And Professor Simpson was like, nah, like, I live up north. So I even had even worse.
So you had to, yeah.
I missed, like, half the semester. And then he still quizzed me on crap that I didn't even come in class to learn yet.
Yeah, I mean, it's tough. So I figure if we could just kind of hit it hard early on, later on when the weather is more stable, then we'll see where we're at. Right, so it's like, man, this guy sucks. He's going to keep us here at 8 o'clock every night. Like, I might still suck. It just has nothing to do with that. Right, so component form of a vector using trig. Right, it's all coming back to the trig. It will always come back to trig. So I'm designating the hypotenuse of this triangle as 1. I'm doing that for a very particular reason, because this triangle is a subset of the unit circle. All right. And the horizontal distance in the unit circle, x, is defined as cosine of theta. The vertical distance, y, is defined as the sine of theta. It's like magic. That's so great. So, if I'm just focusing on the lengths being cosine and sine respectively, what we have is a transition from one triangle to another. It's just scaled up. These two triangles would be in proportion if I bothered making them not identical looking triangles. But what would happen is, in order to get from a 1 to a v, a magnitude of v, I have to multiply by the magnitude of v. So I'm going to do that across the board. So my horizontal distance would be the magnitude of v times the cosine of theta. My vertical distance would be the magnitude of v times the sine of theta. Which begs the question of why I bothered underlining it in blue if I didn't write it in blue. Yeah, and I can't even erase it now. Yeah, well, whatever. I had every intention of color coding it, so that's got to count for something.
Fault is there.
Yeah, it's thought that matters. So the magnitude of v is the length of your hypotenuse. But what we have now is a way of figuring out the length of your components based off of that information. All right? That was louder than I intended. So the component form of a vector using magnitudes, we would say, let me just chuck it here, v cosine theta, comma, v sine theta. All right. Now that scalar rule that we talked about just on the previous page, I think, I did that for a reason. It's to introduce this particular idea. I can factor that out. And get the magnitude of v multiplied by the sine of theta, comma cosine theta, comma sine of theta. Right? So that's an important concept. If we're looking for the component form of a vector, it's an important concept because we're not always going to be given particular dimensions. Sometimes we'll be given an angle. Right? So they're telling us that the magnitude is 4. All right? So they're telling us v. And then they're telling us that the angle is negative 45. So that's our theta. So if I want the component form of this vector, it would be 4 multiplied by the cosine of negative 45, comma the sine of negative 45. Unit circle trig, right? And I hope it's clear in this that I'm not forcing this to happen. Like, this is the natural progression. This is what naturally happens. The Calc 3 makes an awful lot of use of the unit circle. All right, so I'm not inventing problems just to justify the fact that I told you to learn the unit circle. I promise you, it comes up over and over again. So if you haven't made it your business to become familiar with this unit circle, you got to do it. There's an expiration date on this. You're going to get to that point because you're looking at cosine negative 45. Yeah, the calculator can help you out, but if this is a small part of a really lengthy problem, it really helps if you have that information at your fingertips. I mean, at the edge of your brain. So negative 45 is fourth quadrant reference angle. So radical 2 over 2, negative radical 2 over 2. And then I could run through with the 4. I mean, I could have left the 4 inside to begin with if I wanted to. But the component form of this vector would be 2 radical 2, comma, negative 2 radical 2. Because again, you know, it was the joke before, but like, I am not asking you to come in with protractors and compasses. Okay? So if I told you that you had a magnitude of 4 and an angle of negative 45 degrees, and you had to come up with a component form, you're either doing one of two things. You're either converting from polar form into rectangular form, which is essentially what just happened here, which involves unit circle, or you're going to try to sketch this out, which involves estimation, and I don't know how you're coming up with an exact answer if you're estimating the whole way. Right? So you could probably finagle some right triangle trig to get the job done, but it does help if you know these facts. That's what I was talking about before, about this being a fact-based course. You know this information, you're good. If you don't, the opposite of that. All right? So I say this all the time. This stuff, if it looks like black magic, like, where did this stuff come from? I'm talking to you. Go home, study the unit circle. If it looks perfectly fine and familiar, then you're probably not having any trouble with anything that I'm saying, aside from when I screw up a problem.
For Calc 1 and Calc 2, our teachers are usually used when we have like pi divided by 12. Are we going to use that a lot in this
No.
course?
No.
As long as I have the other 3.
Yeah, the other 3. Yeah, the only time pi over 12 is coming into play is if I ask you to graph something, but then I'll give you the graph that has pi over 12 on it.
Okay. I'm good.